Welcome back to Introduction to Operating Systems and Virtualization. My name is Scott Neal. Today we're going to be looking at the fourth lecture in the series, Understanding and Creating Virtual Machines. Today we're going to be covering chapters 3 and 4. If you're following along in the textbook from a course, we're going to be talking about what comprises a virtual machine today, as well as understanding how resources are going to appear in a VM. We're going to be looking at resources at a very macroscopic level. We'll be taking a further look at each of the resources that we'll talk about today in much more minute detail as we talk about configuring each of these resources in both VMware Player and Hyper-V in later lectures. We're also going to be looking at how requests move from a virtual machine through the hypervisor and back again. We're going to be talking about several other things, including Open Virtualization Format, or OVF, and what that means to you, as well as understanding P2V, or physical to virtual conversions. One of the fascinating things that we can do, of course, and one of the things that makes virtualization so powerful is, of course, the fact that we can take a physical machine and actually virtualize it and create a VM from it. So we'll talk a little bit about P2V today. As we wind down the discussion, we'll look at VMware Workstation Player as a virtualization environment, and in the process talk about creating new virtual machines with the product and what kind of files are going to be created that you're going to be looking for after you've created one of those virtual machines. So let's go ahead and get started with the lecture, shall we? So what is a virtual machine? Just to kind of rehash a little bit of what we've talked about in previous lectures, called a review. It is a set of data files that's going to play the role of a physical machine or an instance of an application. However, unlike a physical box, which only has one operating system, one of the beauty of VMs is that even with different operating systems on VMs, I have the ability to run many VMs on a host system concurrently. Virtual machines, of course, see hardware resources that don't exist in the physical world, at least. They are instead created, and then we are negotiating those resources through the hypervisor and going to use the hypervisor to regulate any access to those physical resources that will mimic the resources that the virtual machine believes it has. Of course, if you're inside the VM itself, then the view that you see is going to be pretty much identical to what you would normally see from the inside of a physical machine. It's only when we step outside of the VM world that we begin to notice some dissimilarities, and we'll talk a little bit about those today. Before we move on, I do want to talk a little bit about the difference between a container and a VM. So one of the big buzzwords that you hear today, particularly with Server 2016, now that it's out, is the ability to use containers. So what is a container? Well, containers represent application workloads. So I can use a container either to isolate or pre-configure applications that I want to keep isolated. And I can use those pre-configured applications and clone them and give them to different people and so on. Anyways, they're going to provide a virtual platform for applications to run, primary purpose of a container. There's a big difference, though, between the way a container works and a virtual machine works, and that really is dependent on the location of the virtualization layer. VMs are going to require a hypervisor. The hypervisor, at least in a Type 1 world, sits just above the hardware layer, and it's going to virtually replicate the hardware, while the containers are going to rely on a container layer that's going to actually sit on top of the physical operating system. I guess the crux of this really boils down to containers are going to share a single operating system, where virtual machines will have their own operating systems, and they're going to be relying on the hypervisor to virtualize their hardware components by negotiating those hardware components with physical hardware. So there is a large dissimilarity between the two. Containers do have their advantages. They're generally regarded as a more efficient resource than virtual machines, and they are often going to be quicker to deploy. They have a lower overhead, so there are some significant advantages to using containers instead of just virtualizing everything in a VM environment. To move forward in the lecture a little bit later on, I hope we'll have time to revisit containers in a little bit more detail, because containers are really becoming another one of those industry norms that we're beginning to see. Containers are very important, say, in cloud, how we use cloud technology today. So If you see here, here's a good example of we're talking about similarities and dissimilarities. If you look inside a virtual machine, really, as far as the operating system goes, that virtual machine is identical to any physical virtual machine of that caliber. There is an exception to that. If you go into the device manager of a virtual machine, you will notice some dissimilarities, even though on the surface the device manager may look very similar. You'll notice that a lot of the devices are using generalized industry standard device drivers, or they're using specialized virtual adapters. This is really kind of a hint about the truth of how virtual machines in reality work with the hypervisor and the hypervisor's role in the scheme of virtualization. So just thought I'd show you this very quickly before we move on. So there are, as we said before, in virtual machines we are virtualizing all of the physical resources, and I want to touch on some of those physical resources today. We'll look at each of these in more detail in further lectures, but since we're in the process now of building our first VMs, it's probably a good idea to at least discuss some of these resources and where to find these resource settings, at least in VMware for this lecture. Virtual CPUs. Virtual machines, of course, use CPU. We think they have CPUs like any other machine out there. So virtual machines can be configured to use one or more CPUs just like any physical box. These virtual CPUs, we call them vCPUs, are going to actually, really, if you look at how they work, they are really scheduled time slices on physical CPUs. So the hypervisor is going to be responsible for scheduling the operations that are going to then be passed to the host, processed, and then through device drivers returned back to the virtual machine. So when we think about a vCPU, we'll think about a processor core. So every time you set a processor core up in a virtual machine, think about it being the equivalent to a virtual CPU. There's really, if you look at the machine settings image that I have here, there's really little ability to manage vCPUs other than assign a certain number of processors for the virtual machine to use. It's also very important to realize that virtual machines do not have a one-to-one relationship with the number of CPUs or processors I assign to the virtual machine and what's actually being utilized on the physical host. There's no one-to-one correlation there at all. So it really does boil down to the hypervisor making these calls, negotiating time slices with however many processors are on the physical box. All right. Virtual memory, on the other hand, is slightly different. It's really one of the simplest things to understand because virtual memory is truly mapped to physical memory. However, even though it's going to be mapped to physical memory on the box, it will still be managed by the hypervisor. There are some caveats to that, of course. Being that it's physically mapped to the box, we do have to think about how much virtual memory a machine can have. And the general rule of thumb is to remember that the host is going to require a certain level of memory on its own. And then every virtual machine is going to be able to utilize the leftover memory resources that are available given the number of virtual machines you're running on the physical box, their roles, and their expected needs. You have the ability to alter the memory settings for each of those virtual machines in an attempt to optimize them as much as possible. So we don't want to allocate too much memory to a virtual machine because then we see degradation of the host performance. Likewise, if I assign too little virtual memory to the virtual machine, I'm going to see a degradation in performance in the virtual machine itself. So it really is a balancing act when it comes to memory. This is probably the most frequent resource that is that when we see issues that are resource related, memory is usually what we normally track this back to, either under assigning or over assigning too much memory to a box. Memory is one of the most useful resources we can optimize. So we'll talk more about memory in a further lecture and look at it and talk about ways that we can optimize the virtual machine memory. Virtual networking. Well, like its counterparts, virtual machines, of course, have network interface cards, or NIC cards. They are attached to the boxes. Even though they're virtual NIC cards, we can have as many NIC cards on a virtual machine as you could in a physical machine. This diagram here just gives you a little indication of how NIC cards can be used on virtual machines. VMs do use virtual switches to connect to other devices. Those virtual switches live within the hypervisor infrastructure. There are two types of virtual switches that can be deployed. This is particularly seen in Hyper-V, but we have internal virtual switches which allow us to utilize resources inside the host but not provide physical access to the LAN at large. If we want our virtual machines to be connected to the local area network, then we have to provide an external virtual switch for that connectivity. There are two ways that we can set up external switches. We can set them up in bridged mode. Bridged mode really means that the network traffic from the virtual machine will pass unfettered through the host NIC card and onto the local area network. It will not be altered, not in any serious way, unlike what we would do in a network address translation or NAT mode. Bridged mode allows us to assign or get a DHCP address from the LAN network. It allows that box to act as its own entity on the LAN network, and therefore we can add it to a domain. We can do all the things that we can do to that machine that we could do if it was sitting in a server rack or on a desktop for any user on the network. Network address translation works just like any other NAT box that we would set up. It really is designed to strip the IP address off of the virtual machine packets that are leaving the host box, replace it with the host's IP address packets, and all traffic leaving from the virtual machine will then look like it is from the host. So you can think of it kind of like a proxy server that is, it's going to hide the virtual machine behind the NIC card. There are benefits and caveats to using each of these, and we will talk more about that when we look at virtual networking in more detail. Key thing to remember though at this point in time as we start building out virtual machines is that for most of the virtual machines we'll be building, they're either going to be in bridged or NAT mode. We use the internal switching we can do some neat things with it. For one thing, we can enhance security for virtual machines because the traffic from the virtual machine will not touch the network. So I could theoretically set up two virtual machines as I've done on this diagram here, and if I remove the external virtual switch, I could disconnect it from the LAN and still allow these two virtual machines to interact and see each other in their own little virtual network, which is, when you think about it, really cool. We can even build an entire virtual network. I could have 20 virtual machines, and they're all connected through an internal switch, and then just give them one connection through an external switch to the LAN network, and that would give us a very nice kind of LAN segment for our network. So there's a lot of versatility we can do through virtual switching. Virtual storage, well, virtual machines, like any other machine, have to have storage capability as well. We are, since virtual machines have their own operating system, they're going to presumably have their own data and their own applications installed. That data has to be installed somewhere. And even though that data does reside on a physical piece of hardware somewhere, in reality, that data is stored in files that represent storage devices for the virtual machine. So therefore, if you go into your virtual machine and you look up a C drive in a Windows virtual machine, you'll notice that C drive is going to be probably significantly different than the properties of it compared to the C drive properties on your host machine. So if you set up a 60 gigabyte virtual machine hard drive and you connect it, then you may notice that drive when you move it to a flash drive or something, your virtual machine, you want to take it home, you'll notice that it only takes up 14 gigs or 13 gigs. Well, that's because we have two ways we can set up that storage space. We can set it up as a static storage space where we allocate all the space at once, in which case if you tried to move it, it would be 60 gigs and probably too big for your hard drive. The other option is to set it up as dynamic, which will only be allowed to use the space that contains data. That makes the virtual machine much easier to move, because in actuality it's only going to be as big as the current amount of data stored on the device. So by default, particularly in VMware Player, this will be a dynamic drive that's set up. VMs, of course, are not typically concerned about the connection to the storage medium. It doesn't really worry if it's SCSI or what type of, what kind of connection speed. All that is negotiated through the host. So that's another benefit of using virtual machines. Virtual machines are they're quite versatile. They're very flexible. There are some things that I can do with virtual machines. I can multiply them in various ways. Cloning, for instance, is the process of duplicating the virtual hardware and all of the software for a VM. And then I can take that clone and I can build multiple VMs off of that clone for various purposes. I can do a similar thing with templates. Templates, on the other hand, allow me to create a virtual machine that once I've declared it as a template, it will no longer run. It is an empty virtual machine at that point that's going to act as a standardized mold for me to create new virtual machines. This is great if you're running some sort of cloud enterprise network and you've got pre-configured templates set up for your clients they can purchase, and then you can just deploy these templates as you see fit. Snapshots really isn't quite like multiplying, but it is a fantastic quality of virtual machines that really add to the redundancy and reliability of them. Snapshots is the process of capturing the present state of a virtual machine that can then be used to restore the virtual machine to that state at any other time. So if I want to, say, test malware on a virtual machine, I could create a snapshot at the very beginning when I first configure the virtual machine, start all my testing tools, run that piece of malware in that virtual machine, record what happens, and then when I'm done, I can just revert back to the snapshot, and then the box would be clean again with no malware on it, and it'd be restored back to that original state for me to do additional testing or to try out another piece of malware on it. Or if the box becomes corrupted, maybe I have a server and it gets hacked, or I get a server and something gets corrupted on the operating system. If I've been taking snapshots routinely, then the amount of work that I will lose is minimized, because I can just simply go back to the last snapshot before we noticed any problems, restore that snapshot, which just takes a moment of my time, and I am back in business. So snapshotting is really a great way of allowing us to build redundancy on the servers or on any type of VM that we create. So the ability to multiply, restore these systems using these technologies makes virtual machines much more flexible and resilient than their physical counterparts. It is one of the many reasons that virtualization is becoming the industry norm. Alright, let's move on to Open Virtualization Format, or OVF. So what is OVF? OVF really is just a method of packaging and distributing virtual machines. It is designed through industry standards as a vendor-neutral industry standard, which means it's totally cross-platform. It's cross-vendor. It's cross-platform. It's cross-vendor. So I can take an OVF package and should be able to deploy it to virtually any vendor's virtualization environment that I choose. It is really used for exporting and importing virtual machines, and if find an OVA file. That OVA file is really just a bundle of all the multiple VM files that have been bundled into one file package for deployment. So whenever, that's what the OVA extension is for. It stands for Open Virtual Appliance, or some people call it application. And if you see an OVA file, what you're holding in your hand is a virtual machine import file that you can use to import a virtual machine that someone has given you for whatever purpose that machine is for. So that leads us into P2V, the physical to virtual process. There are applications out there that we can run on physical boxes that, once we run it, will build a virtual machine modeled off the physical machine it's running on. That virtual machine in turn can then be saved on any other volume or any other remote storage that you choose, provided you've got access to it. There are some benefits using P2V. It's great for consolidation and containment strategies. So just a reminder that consolidation is all about removing the physical servers from a data center by virtualizing them into fewer hosts. So that's one option that I can do using the P2V process. If I'm using the containment strategy, then I may be deploying new applications directly into a virtual environment. So P2V is a tool that's specific for consolidation and containment strategies. We'll be demonstrating some P2V here in the near future. P2V will require installing utility on the host, of course, and then you run that utility, and usually the time it takes to virtualize that machine is going to be dependent on several factors: the type of machine that's running on, the size of the machine, where you're storing that P2V image to, and so on. So it's not uncommon for this process to take several minutes to several hours to complete. But once it's completed, you have a functional virtual machine that is modeled off of the physical machine that you are running, and that gives you some significant benefits. So there's also a difference between hot cloning and cold cloning. Probably ought to differentiate between that before I move on. Hot cloning is all about creating a virtual machine while the workload is active. That's just a fancy way of saying I've got the box running. And so there's no application interruption that's going to be needed for this box. So the box, in theory, can be running and serving clients, customers, while I am physically cloning or doing the clone of the box. There is going to be some issues with that. If I clone a box that is a hot clone, there's no 100% guarantee that the box is going to be 100% cloned like it was when we initiated the cloning process. So that's just an important thing to remember if you choose to do hot cloning over a cold cloning process. Cold cloning, on the other hand, allows you to be virtually assured that the box will be in the same pristine state that it was when you began the cloning process. This means that I have to shut down the application, make sure it's inactive, and so that's going to be another option that's available to us for the cloning process. The virtualization, of course, is very flexible. We've talked about physical to virtual, but there's also virtual to virtual, and I can even do virtual to physical processes as well. So virtual machines allow for a lot of versatility in deployment strategies. So let's look at VMware Player. VMware Player and VMware Workstation are two components that were two virtual machine applications that we're going to be utilizing for the course. VMware Player is a Type 2 hypervisor, as we reiterated in an earlier lecture. I can create, manage, and run virtual machines. It's available as a free download at www.vmware.com in the download section. And as a Type 2 hypervisor, of course, it's going to be pretty much installed just like any other Windows application, provided, of course, you're not running Hyper-V on a Windows machine already. They are not compatible, and it will tell you that you'll need to uninstall the Hyper-V feature on your operating system. You also have to, of course, have virtualization as an available component in your BIOS on your machine as well. It is simple. There are minimal configuration options in VMware Player compared to VMware Workstation, even though we have seen significant improvements in Player in recent years. VMware Workstation is certainly more full-featured than the Player. There are other popular tools out there. VMware Workstation, of course, and Fusion are both VMware products. Workstation is, of course, a paid-for product. It is the primary Type 2 hypervisor environment that they would prefer you use. VMware Fusion is for Macintosh users. Parallels Desktop, VirtualBox, Microsoft Windows Virtual PC, Hyper-V. So there are several different types of virtualization applications out there. If you're going to be creating new VMs, and we will be creating new VMs are going to be associated with containment or development strategies. So that's the purpose of creating new VMs. Creating a new VM builds only the virtual hardware. So the VM itself, by default, all you need is the virtual hardware that's created. That means that there are lots of options that are available for new virtual machines. I can choose to have, as we will in most of our scenarios, choose to install the operating system at the time we build the virtual machine. We can opt not to have the operating system installed at all. We could not have a virtual disk built at the time that we create the virtual machine, opting instead to bring in a virtual disk from another source and hook it up to the VM that way. So think of the new virtual machine as a bare metal box, physical box, that, you know, when you build it, provided you haven't installed an operating system on it, it's just a bare metal virtual box, and I'm capable of doing anything with that virtual machine that I could do on a physical server without an operating system. So adding devices, once we've created a virtual machine, I can go into the virtual machine settings and change the hardware devices that are added by default. So the memory, of course, is something that you pre-configure as part of your build. Your processors are something that I can configure after my build. I can add floppy drives, network adapters, any USB, any of these things that you see on the screen here are able to be modified or added or even removed in some cases from the virtual machine, just like you could on a physical machine. So if we're going to be creating a new VM, it's really going to be all about creating the virtual hardware. So you need to think about how many CPUs you're going to need, how much memory you're going to need, how much storage you're going to need, because once you've made those decisions, the process itself is pretty much a wizard-driven process, at least in VMware. So for our example, we're going to remember to select store the virtual disk as a single file. We have the option of doing it as multiple files, which supposedly makes it easier to move the virtual machine to another computer, but it may reduce the performance if you're going to be running it on very large storage spaces. So when we've created the virtual machine, what virtual machine files are there? Well, I want to run through some of these. One of the most important virtual machine files is the primary configuration file. The primary configuration file can be identified. It looks like three little windows if you're using VMware, and it's going to be basically the name of the VM .vmx. I can launch the VM by double-clicking that .vmx file and launch it in my VMware Player or Workstation. I can open that VMX file in Notepad, and that will allow me to make some configuration changes, because this is just a kind of an ASCII text configuration file that dictates how that machine is going to start up and what parameters it's going to run on. The log entries have a .log extension at the end of them. They really just log all the workstation activity, primarily used for troubleshooting. There's also, you'll see a .nvram file in your mix of files as well. And its whole purpose is to store the state of the VM's BIOS. The .vmdk files, these are another primary group of files you need to be aware of. These are the virtual disk files storing the contents of the virtual machine's hard drive. And you may have different sets of these files depending on how many hard drives you have installed in your virtual machine. There's a few others out there. There's the .vmdk, it's a redo log file. It's created when snapshots occur, as well as the .vmsd, which is the snapshot metadata file for your VM. The .vmem file is the virtual machine's paging file. You're only going to notice this file when the machine is running. When you shut down the machine, this file will disappear. If you have a suspended state file, .vmss allows you to return your box from its suspension by recording the actual suspended state of the box at the time you suspended the machine. There's also a couple different types of team files out there. The .mtm VMTM team data configuration file is one of them. So if you look at a typical folder for, this is my server 2012 folder here, you'll see that I have pointed to the primary configuration file, and I've also outlined, in this case this is one disk that's been virtualized as many files, and you can see that the disk file and the configuration file are here, as well as some of the other files that we have talked about in the previous screen. So let's summarize very quickly. Virtual machines run on top of a hypervisor responsible for duplicating the hardware, while containers are going to be isolated, allow for isolated and virtualized applications to run on top of a single operating system. From a user or an application standpoint, VMs are going to look and act like physical boxes, but thanks to duplication and redundancy features, they're far more flexible. VMs are incredibly cost effective, and if you're looking to import or export VMs in and out of environments, you're going to be looking for OVF or OVA files. This is really the standard that's going to be allowing for cross-platform and cross-vendor distribution. And if you use a P2V application such as VMware's P2V converter, which we will be demonstrating, you will see that one of the options is to store this as an OVF or OVA file. So, P2V technologies provide rapid and automated method of moving existing physical server workloads to virtual environments. And the VMware Workstation Player, of course, just as a reminder, are Type 2 hypervisors, not the Type 1 hypervisors where it sits on top of the hardware layer. Alright, so that's Lesson 4 in a nutshell. I look forward to seeing you when we talk again in Lesson 5. Thanks a lot.